Hi everybody, and welcome to part 3 of the demonstration for the angle plate project in Machining 210. Today we are starting with step number 9, which is laying out the part for the hole location. So today we're going to be drilling and reaming a hole and using the vertical bandsaw to remove a bunch of material. And then next time we're going to blend the inside surfaces to that hole to create our little radius in the inside corner. Okay? Let me go ahead and draw what the part looks like right now, because we have to do a little bit of calculation in order to figure out exactly where that hole is supposed to be located. Looks a little something like this. Kind of, sort of. Something like that. Okay. So from the print, we get some information, like this dimension right here is 2 inches 400 thousandths. This dimension right here is 1 inch 880 thousandths. This is 500 thousandths. This is 630. And it also gives us this radius right here on the inside corner as 218 thousandths. 218 thousandths. But this is not currently what the part actually looks like, right? Right now, all we did was square up the block and get it to its overall roughing dimensions, so 30 thousandths of an inch over all 3 of the overall dimensions here. So what we need to do is, let me actually go ahead and draw in what it looks like right now so that we can kind of see a little bit visually how we're going to get the finished part from the rough block that we've got at the moment. I'm going to try to be careful here. So that's kind of like what we've got right now. Okay? We've got a little bit of extra material on the overall dimensions. So basically we have a little bit of extra material on all of the surfaces because we still need to finish everything. Remember that because of the internal stresses in the material, when we go to cut all this material out, this whole thing's going to spring open. And so we left a little bit of material on all the surfaces to finish afterwards. We left nominally 30 thousandths of an inch on all the overall dimensions, but, you know, it didn't come out to exactly 30 thousandths of an inch oversize, right? It's just pretty unlikely that it would. So what we need to do to figure out where we need to put that part, or where we need to put the hole, is figure out exactly what our overall dimensions are right now. It's okay if they're a little bit off, but we need to account for that in our calculations. So let me go ahead and measure the part with a dial caliper. Okay. So the hole is actually going to go into either side 5 or side 6. And so let me go ahead and measure this. This says 2 inches 428. 2 inches 428 in this direction. Let me go ahead and measure this direction. So that says 1 inch 906. 1 inch 906. Okay, so this was supposed to be 1 inch 910. I'm 4 thousandths away. This was supposed to be 2 inches 430. I'm 2 thousandths away. That's totally fine. We weren't trying very hard to hit those roughing dimensions, right? So it's okay. So in order to figure out now where to place that radius, sheet number 2 of your print has this extra information for the roughing geometry. It shows you where the material is to be removed with the bandsaw. It shows where the hole is, because of course this radius is going to start off as a hole. And then we're going to remove material, all this material here, with the bandsaw. So we're going to cut to the center of this hole and remove all this material. And then we're going to remove this extra material here. So this is just going to be a bandsaw cut. Then we're going to remove this material here with the mill to blend it to those tangent points of the radius. And that's how we're going to get the radius, right? But it starts its life out as a drilled and reamed hole. So of course the diameter of that drilled and reamed hole is going to be twice the radius. So if you do 218 times 2, the diameter would be 436. But remember that these are rounded off values. So actually what we're going to do is go in with a 7/16 reamer, which is 437 thousandths and 5/10, 437.5 thousandths, right? So pretty close. All right, that's just the size that we're using. But actually, the number that we want to calculate where the hole is supposed to be is the radius, right? Because remember, the radius is the distance from the center of the circle to anywhere on its circumference. Okay, so that's how we're going to find our position. So that sheet in your print gives you the formula for finding out where the center of the hole is going to be located, because of course the drill is going to be positioned based on the center of the hole, not based on its outside edge. That's just, you position the spindle where you want the hole to go, but it's the center of the hole that you're positioning. So that's why we need to do this math, because the final part gives us dimensions from the outside edge of the hole, but we're going to be positioning the hole by its center. So that's the calculation. And that sheet in your print gives you that information, the formula that you have to use. Okay? And essentially, it's this. We're given 630 thousandths from the bottom of the part to that position right there at the edge of the hole. That's 630, so that's fine. Nothing weird there. Then to get from the edge, we have to add the radius. The radius from the circumference gets us to the center, so that's also nothing special. But we have to account for this extra material that we left on this surface right here. Basically what we're going to do is we're going to take the single-sided finish allowance, and that's going to be starting with this number actually. So this is our overall dimension for the height. Okay, and this is the direction that we're positioning the hole for this calculation. So we're going to base it off of this. All right, so we are at 1 inch 906. We're going to end up at 1 inch 880. So the overall amount that we have extra on this dimension is 26 thousandths. 26 thousandths. All right. But that accounts for material that we have on this side and on this side. But we only need to account for the material on this side, right here at the bottom. So actually, we're going to take this number and divide it by 2. Just split it in half, and that gets us 13 thou. Okay? And that's this amount right there, 13 thousandths of an inch. That way, we position the hole a little bit further from this surface, and then when we cut off that 13 thousandths, now the hole's going to be in the right location. Does that make sense? Okay. So then we have to add all these together. 630 thousandths plus 218 plus 13 thousandths gives us 861. We also have to do that in this direction. okay? Because of course, the position of a hole has both like an x and a y coordinate, right? It has a distance from one side and a distance from another side. So we have to calculate that as well. So I'm going to have to go ahead and erase this here because I need to draw up there. All right. So I'll just draw what I had over there for this side as well. There we go. Okay, so this dimension right here, we know that's given to us. That's the wall thickness, 500 thou. We also know the distance from that surface to the center of the hole because that's just the radius. So again, 218. But this distance right here, this extra amount that we left on this surface, that is based off of this real number right here that we measured off of the part. So the calculation is the same. 428, our current measurement, minus 2 inches 400, which is the ultimate number that it's going to come out to in its final size, gets us 28 thousandths of an inch. But that accounts for the material over here and over here on both sides of the part, right? So we only need to account for this material right there. So again, we're going to take this number, 28 thou, and divide it by 2, and we get 14. So we add 14 thousandths. So let's do that calculation. All we need to do is add it all together again. 500 thou plus 218 plus 14 thousandths, 732. So 732 thousandths. Let me go ahead and erase some of this other information so that we can be left with just what the part should look like at this stage. So we're going to put a hole with a diameter of 7/16 of an inch, 0.4375, 437.5 thousandths of an inch. And we're going to put it 732 thousandths from this side and 861 thousandths from this side. Then we're going to cut this material out on the bandsaw. That's what we're going to do. So let's go ahead and go over to the workbench, and then we can blue up the surface and then take it to the surface plate and actually lay these lines out so that we have something to follow, and also so that we have something as like a sort of visual check when we're locating the hole on the milling machine. And you'll see why. It has to do with using the edge finder and some quick calculations that you have to do. But you'll see that in a moment. So it's very important that you mark up the correct surface, okay? It's sort of like human nature to think that the hole goes through the largest surface on the part. Or at least I think, because a lot of people make that mistake. But that would not be correct, okay? So it should go on either side 5 or side 6, and that's because, as you can see from the print, the hole goes through the surface, which is 1 inch 910 by 2 inches 430, right? So that's side 5 or 6. Right there is 1 inch 906, and that right there is 2 inches 430, okay? So this is the surface that we want. And you can use either the red or the blue dicum for this. I prefer the blue dicum, but you know, that's just a matter of personal preference. I find that it shows up a little bit easier. Make sure that you shake that up before you apply it, and then you just paint the whole surface there. The whole surface. Yeah, another reason why we like to lay this out is because a lot of people will do the calculations based off of the correct measurements, but then they'll get to the machine and they'll orient the part with the large surface, either 1 or 4, facing up. And then they'll drill the hole in the incorrect location. Frustrating. Now we just need to let that dry, and then we can take it over to the surface plate. It's very, very important that this surface plate is clean, and that's just sort of a general rule that should be followed. We have this surface plate cleaner that you can use. It's basically like some kind of a Windex or Windex clone, and you can just spray that down and then get some of these Kim wipes. These are sort of lint-free wipes that are really handy for cleaning off precision surfaces like this. You can see all the crap that comes off of there. These get really dirty. You know, oil and dirt, but also chips and other things like that. And it's really important to get this nice and clean. Otherwise, your part's going to be sitting on top of all of that dirt. And you're not going to get good measurements. Your layout lines are not going to be in the right place. And I always tell people this, and you know, sometimes people just don't believe me. They think I'm exaggerating or I'm just being a jerk. But then their parts come out bad and they come running to me asking for help. And I tell them they should have paid more attention during the cleaning stage. Cleanliness is very important when it comes to machining. There we go. So even though these are lint-free wipes, really probably the best way to check for cleanliness is, see, it still leaves a little bit of like pilling, some lint on there. Best way to check for this is just to use the meat on your palm. It's a very accurate schmutz indicator. Let's go ahead and get all that crap off of there. That looks pretty good. Okay, parts clean. We're going to use the scriber on the height gauge to scribe out some lines on that surface. And just as we did before, we're going to zero set the bottom of the scriber to the surface plate so that we can get an accurate distance from the surface plate. That's how we get our accurate positions of our lines. And we're going to zero it out over top of a shim. This is just a 2/1000 shim here. You can tell because it says 2/1000 on it. Doesn't matter what size it is, but you need to know what the size is. So if it weren't labeled like this, you could just grab a micrometer, give it a quick reading. And the reason we're going to do this is, well, you know, it would be easy to just set it directly off of the surface plate, but then you don't know when you sort of bottomed out. And if you over travel, then actually you're going to be sitting on 3 points. Here, on the back side over here, and here on the scriber. And you're not actually going to be sitting everywhere on the base, and so you're not going to get an accurate touch-off with the scriber. So the shim just gives us a little bit more sensitive touch-off there where we can feel a little bit of a tug. Like right, there it is. Just a little bit of contact. It still moves in and out nice and freely, but you can feel a little bit of contact, and that's actually where we're supposed to be touched off. And you can see that the dial right now is actually not set in the correct location. So whoever did this before didn't set it correctly. All right? So I'm going to set the dial not to 0, but rather to 2/1000 of an inch over the 0, because my shim is 2/1000 in thickness. And now I'm going to hit these two little plungers, and then that'll zero out the digit counters. So now if I were to remove that shim and move this scriber down to where the dial or where the needle on the dial says 0, so that would be where the scriber is actually touching the surface plate, but just touching, right? Not over traveling and knocking the base off of the surface plate. Anyway, so that's how you do that. But so what's the actual distance that we need to set? So we had calculated, let's do this direction first, from here to here. So that's going to be 861 according to the calculations. So that's going to be 100, 200, 300, 400, 5, 6, 7, 8, and 61. Right around there. Okay, so each one of these graduations is 1/1000 of an inch. There are 100 of them in one revolution, right? So that's 100 thousandths. And so here on the digit counters, it reads 100,000ths of an inch. So 0.1, right? 1/10 of an inch, 100 thousandths of an inch. All right. So then I'm just going to go ahead and scribe a line all the, oh, that's kind of loose. There we go, all the way across the surface, and now we have that position there. So let's go ahead and do the other direction. Okay, so now we've got 732. So that's back at 800. There's 700, so 732 right there. And let me go ahead and mark that off as well. Boom. So that is where our hole is supposed to go. But I'm going to go ahead and also mark down the lines for where the tangent points are going to be, okay? And that's, again, just so that I have a sort of visual indicator that I can use as a double check, but also so that, I think I'm going to show you two different ways to blend the radius there. And one of the ways is going to be just lining up the cutter with the tangent points by eye. And so for that, I'm going to need some extra lines there. So let me go ahead and mark those in. So that would be this number, right? So 630 plus the hole radius plus the finish allowance, but without the hole radius, right? So just take the hole radius out of the equation. So really it's just the wall thickness plus the finish allowance. So 630 plus 13 is going to get us 643. So let's do that. Go back to 0. Okay, so 3, 4, 5, 600, and I said 43 right there. Go ahead and mark that out. Okay, and then 500 plus 14 in this other direction. So go back to there's 500, 514. And mark that off as well. Okay, very nice. Now we can go take this over to the milling machine. Okay, as always, we need to make sure that everything is real nice and clean before we put the part in against the fixturing surfaces. So I'm going to reuse these same parallels I was using before. They are perfectly adequate for this purpose. Okay. Then we want to make sure that the dicam is facing up, just like that. Clamp that down, and we should tamp that down on the parallels also. Make sure that it's sitting nice and square in the vise. Good. All right, we're going to use the drill chuck here with the R8 taper on it. It gets installed just like all the other tools. Just try to get the little key in there to line up with the keyway. I'm going to use a keyless drill chuck because they're so much more convenient. But you can also use the Jacobs chucks. You'll notice that the Jacobs chucks actually don't run out quite as much as these keyless drill chucks do. They're just a little bit better quality. Okay, but it's not going to matter much for what we're doing right now. Okay, and that takes a 3/4 inch wrench to tighten the drawbar. Very good. I'm going to have to bring this down a little bit because the drills and the reamers take up so much room. I mean lengthwise, vertically. So you got to give yourself a little room. I'll probably have to move it again once I put that reamer in there because the reamer is very, very long. Okay, let me just go ahead and drop that a little bit more. All right, so we are currently on step number 10. Find the hole location on the mill using the DRO for digital readout, and we're going to use an edge finder, this thing right here. So this goofy little tool has a cylindrical shank, and then it's got this sort of wobbly bit on it. That is actually just attached with a spring to the cylindrical shank. It goes into the drill chuck like so. And the way we use this is we spin it up to no more than 1,000 RPM. Okay, I'm going to go ahead and do that now. There we are, 1,000 RPM. And that's just so that that little tip on the end that's only held in by a spring doesn't come flying off. Okay? Now, when that little tip there gets pushed to the center of the shank, it wobbles out less and less and less. It becomes more and more concentric, right? But if there's nothing to push it towards the center, it can wobble out like that. And that's actually the basic way that we're going to be finding these edges. So let me show you. Let me find this side first. I'm going to bring this down with the quill. And we're going to touch off with this little reduced diameter right there. And if it's not, if it's not wobbling out like that, you should just go ahead and try to get it wobbling a little bit. It'll make it easier to find the edge. Then we're going to move the table so that we get closer and closer and closer to the edge finder. So it's actually touching that surface. And we keep going closer and closer. You can see it's wobbling out less and less and less, becoming more and more and more concentric until, I'm going real slowly now, until, wait for it. There we go. It just popped out. Okay? So once it pops out like that, you have found your edge. And actually, if you reverse the direction of the spindle, it'll pop out the other direction. See? So sometimes it's easier to see that, right? It's a little trick that not everybody knows about. Now I'm going to go ahead and hit the Y digital readout to 0 that position, and then I'm going to double check it again. Knock it out a little bit, move in. Nice and slow. Okay, and my digital readout is reading the same value. Okay, so that's a good touch off. I'm going to bring this back up with the quill. And now we have to discuss something. All right? So we just touched off on the edge of the edge finder. But what we're trying to do is find the edge of the part with the center of the spindle. Okay? So in order to find the center of the spindle, we need to move over a distance equal to half the diameter, or the radius, of this little cylinder that we touched off on. Now, these cylinders here are ground so that they are 200 thousandths of an inch, very accurately, okay, 200 thou. So we need to move over 100 thousandths. I do that so that it makes the math easy, all right? So we have to move over 100 thousandths, okay? Let me show you kind of close up what it looks like. On the digital readout, move over 100 thou, exactly 100 thou, right there. And then I'm going to re-zero the Y on the digital readout. And now you can see that the center of the tool is directly over the edge. And that's what we want. That's what we want. Okay? Now I can move my distance to the position of my hole. And that was 861 in this direction, all on the digital readout, right? 861. Right there. Then I'm going to lock down the Y-axis so that it doesn't move. Okay? Now what I need to do is touch off on the other side. So start it back up again. Knock it out, bring it down, move over. Nice and slow. Okay, it popped out the wrong direction, so I'm going to reverse the spindle. And now I'm going to zero out my X on the digital readout. And again, I'm going to go back in and double check my touch off. Gets closer and closer and closer, more and more and more concentric until it just pops out. Just pops out. You don't want to over travel. But there we go, right there. Double check my position on the DRO, okay. It agrees within 0.2 of a thousandths. I'm happy with that. Okay, go ahead and zero this back up. Okay, so there are two ways to do this, right? Either you can just add 100 thousandths and, either you can physically move 100 thousandths and re-zero the digital readout, or you can just add 100 thousandths to your overall measurement, right? And that'll get you to the same location. So I'm supposed to be 732 thousandths from this side to the center of the hole, so I could just go 732 plus 100 thousandths of an inch is 832, so I could just go 832 like this. Oh, over travel just a little bit, go back some. And there I am at 832, and you can see that that got me to the same location, right? The way that, one of the reasons that we wanted to use these lines and scribe the lines in the top of the part like this is so that we could have that quick little double check. So I just put the center drill into the drill chuck, and now I'm just using it to scope out whether or not the center of the drill lines up with those lines that I scribed, so at the crosshair, and it does. Okay? So that's my double check right there. Now, if you're going to get the hole position off on this part, it's very, very likely that you're going to be off exactly 100 thousandths because you forgot to add the radius of the edge finder. It's a very, very common mistake, even amongst the professionals. So it's nice to have these lines here to double check yourself. Okay, now we're on step number 11. That's center drilling the hole here, just to give the drill something to locate it. Okay, we spin that up at somewhere between 600 to 1,000 RPM. I'm already at 1,000 RPM, so I'm going to go ahead and start that. Little bit of coolant, and then just bring that down. We don't need to go very deep, just to kind of put a little mark there for the drill to follow. You can clear those chips there. Clean the coolant off. And this is, again, just a quick check to make sure that where that little center punch mark is, or center drilled mark is on center of the crosshair, and it is. It's good. Next is the letter Z drill, which is 413 thousandths. Is that right? Let's see. Z drill is 413 thousandths according to my little drill gauge there. Very handy. Okay, that goes directly into the drill chuck as well. And so you can see that I'm going to have to move the table down a little bit in order to get that to go. I'll probably have to do it again for the reamer. Okay, lock that in. I'm not going to tell you how fast to spin this for step number 12 because it's something that you should have calculated, okay? But I'm going to go ahead and set it to the correct speed. All right, and give it some coolant. This is such a long hole that I'm going to need to not only kind of break the chip every now and then, but I'm also going to have to pull the drill completely out of the hole from time to time to get a little bit of coolant in there. Okay? You don't just want to bury this down into the part continuously because you won't get a good result. There we go. Okay, so every time the chips get about as long as the drill, then you're going to want to back them off a little bit. Just like that. You know, and if they adhere to the drill like that, go ahead and turn it off. and clear the chips. Don't try to clear the chips while the thing is spinning. You know, sometimes they just do that. And then again, like I said, we're going to try and break the chips. You know, whenever they get about as long as the drill. And then periodically, we're going to clear it all the way out from the top of the part and then go back in. Just trying to get some coolant in there because it's a very, very long hole. A little bit more. There we go, all the way through. Clear those chips just to get everything nice and clean. Okay, time for the reamer. Reamer goes in. Again, you can see that it's way too long, so I'm going to have to drop the knee considerably. All right, is that going to go? Yeah, there we go. Okay, again, I'm not going to tell you how fast, ooh, wow, maybe a little bit more. I'm not going to tell you how fast to run this thing because it's something that you should calculate, but sort of just a general rule of thumb is that reamers are run at half the speed of the equivalent size drill. There's a little thing to know. I'm going to use tap magic for this instead of coolant and apply it liberally. Now here's the deal. I'm not going to do this all in one shot because as I mentioned in the lecture portion of this video, there is some quite a lot of material to come out of this hole right now. So I'm going to do it in, I don't know, maybe like 3 steps or something. Because the material that comes off is going to load up the flutes of the reamer. And if it loads up too much, and all it's going to do is get, you know, those chips are going to drag around inside of the hole and it's going to chew up the inside surface. And we'd really like to get a nice surface on here, the best that we can. So again, I'm going to stop it at some point and pull it out and clear the chips. And actually, take a look at this reamer. It's really wobbling around right now. And this is pretty normal. These reamers are made so that the shanks are very, very long. And they're, you know, it's kind of known that they're going to run out a little bit, but they are designed so that they will always follow the drilled hole. So even if it's running out right now, as soon as you start cutting, it'll center back up again super fast, right? So, you know, sometimes I see people, they'll like cut the shanks off the reamers and hold them real close to the cutting edges. But that's actually not how these work. They're supposed to wobble so that they always follow the hole rather than following the spindle, if that makes any sense. Here we go. See that? It found that hole perfectly. And I can feel just a little bit of resistance right there, so I'm going to pull this out. Clear it off. Okay, let's go back in. A little bit more tap magic. Okay, I can feel it dragging again right there. paper chips. And let's go again. One more shot of tap magic. All right, there we go. I'm through. That's it. Okay. So now we can take this thing to the bandsaw and remove all this material right here. Okay, so this is the vertical bandsaw. And as I've mentioned before, this is a very efficient machine, as well as being a very versatile machine. And the way that it works is pretty simple. So we've got two wheels, one on the bottom, one on the top. The bottom wheel is the driver wheel, and this up here is just an idler wheel. And then we have a continuous bandsaw blade that runs between them. So there's the bandsaw blade right there. You can adjust the position of these guides right there just by loosening this knob and then tightening it down. So now you can see the bandsaw blade a little bit better. Okay, so it's really just a continuous piece of stock, or rather it's coil stock that's been snipped and then welded back together and then looped around here. And then the idler wheel is really used to set tension. So you can move the idler wheel towards and away from the driver wheel, and that's how you can set the tension on the blade. But otherwise, that's really all that's going on. Let me turn it on real fast. I'll show you kind of how it works. There you go. So that's a relatively slow speed. Okay. Here's the start-stop button right here. So start, stop. Nothing super fancy there. A lot of people wonder what this thing is. This is actually a bandsaw blade welder, and a lot of these large vertical bandsaws have these built into them, although you can also buy them as separate standalone units. And so this is so that instead of buying pre-welded bandsaw blades, you can just buy some continuous blade stock in coils and then cut it off to whatever size you need, okay? And so here you've got a little belt cutter on the side. Then you would put the two ends of the bandsaw blade in these two little clamps right here, and you can set a distance, and that essentially sets the resistance of the two electrodes, right? And then this is just a resistance welder, right? So it's just heating it up through electrical resistance. It has an anneal setting, so once you weld it together, it's going to be kind of hard and it's prone to snapping right at the weld. So then you can anneal it by just heating it up to a certain temperature that is usually governed by looking at the color that it heats up to. And then there's a little grinder here on the bottom that you can use just to grind off any kind of weld bead. And then you've got your nice continuous bandsaw blade stock, or bandsaw blade. One kind of neat thing that you can do with these, more than just saving money on bandsaw blades, is that if you've got a part that's got a profile on the inside of it, like maybe a big plate that's got a profile in it, if you try to cut that profile out normally with the bandsaw, you'd have to cut from the outside in order to get to the inside there. And so you would have a slit wherever the bandsaw blade entered. But if you pre-drill a hole through the part, and then snake a piece of bandsaw blade stock through there, then you can weld it in place with the bandsaw blade already inside of the hole, cut the profile out, and then snip the bandsaw in order to remove it. So that way you can create an internal feature without having to cut from the outside. That's kind of cool. It doesn't come up very often, but it does come up sometimes. So what speed do we actually want to set on this thing? Well, that really depends on the material, and this chart on the front of the bandsaw actually is pretty accurate. It works pretty well. So we're going to be doing cold rolled steel right there. So that's 125 to 200 SFM, surface feet per minute. So that is, because it's not a rotating tool, right? It's a linear linear cutting tool, and so we get a surface feet per minute. No need to do any calculations to convert this into an RPM. That's not how you specify the speed. So that's actually quite easy right there. So how do you actually set the speed? We've got a high and a low gear and a neutral in between. And then down here we have a continuously variable speed adjustment, right? So this actually works just like the Bridgeport milling machine head does. Okay? So first we select a high-low gear. All right, so we're going to be in the 125 to 200 range. So that's definitely going to be on the low speed side. So low gear is good. If you need to change, you pull this knob out, move it over to whichever position is desired. And then a lot of times, it doesn't actually quite go into place. And so you can, by hand, sort of move the bandsaw blade until it lines up. Okay, same is true in this direction. Again, that doesn't line up very well. Just move the bandsaw blade by hand until it locks into place. Okay, then just like the milling machine, in order to adjust the continuously variable speed knob, you have to have the bandsaw on. I'm going to go ahead and move this out to, here we are. So the inside reading is for low speed, the outside reading is for high speed, so that's 125 right there, and I can be anywhere from there to 200. So I'm just going to go to 150, that sounds fine, all right? So here's something that I think is worth looking at. This is the back of the bandsaw with the cover removed. So that over there is the pulley that drives the driver wheel on the bandsaw. And then this right here is an adjustable speed pulley. So it's got two cones and they move into and away from each other in order to change the diameter. And actually there are two of them, there and there. And that changes the diameter of the pulley. Right, and so you change both of those pulley diameters. This is actually the one that is adjustable, then the other one just sort of follows along based off of belt tension. But that's how you can change the diameter ratio between the pulleys, and that's how you change the speed. So let me go ahead and spin this up, and then you can see what's happening when you actually change the speed on this thing. So that's pretty cool, and this is worth looking at because this mechanism is extremely similar to the one that you will find in the Bridgeport milling machine. So harder to take that apart to look at it, but relatively easy to look at this, so I think it's worth it. So the bandsaw blade is kind of flimsy, and it needs to be supported by guides. Both on the top and on the bottom. So up here you can see there are these two little ball-bearing guides that sandwich the bandsaw blade on either side. And then down here, there are also some guides either side of the bandsaw blade. Okay? And it's important to try and position the guides as close as possible to the part so that you shorten up that distance between the guides, and it just makes this a lot less flimsy. These can also be adjusted to sandwich them closer together. So yeah, there's a little bit of a gap right there. Maybe it needs to be adjusted. So you could just go straight in, with the part into the bandsaw blade like this and sort of try to guide the part around by hand, just following that line with your eye. But a better way to do this is to use the guide rail right here. That's what it's there for. And by the way, I'm going to cut, let's see, which side am I going to cover? I'm going to cut this side first, right there, right to the center of the hole there, and then I'm going to cut this side. And that's just because if I were to cut this side first, right, well then in order to do the other side, the side that I just cut through is going to be up against the guide rail, so there's going to be a burr right there. So it's not going to sit perfectly square. And so if I do this side first and then I do this side, well, I've got a nice machine surface here to follow on the guide rail. And so that just, it's a little nuance that helps get better precision. Anyway, so I'm going to do this side first. All I have to do is kind of line that up by eye and then lock the guide rail in place with this knob right here. And I don't know if you can see this, but when you tighten this, it kind of moves around a little bit. So you got to double check to make sure that it's where it needs to be, and that looks pretty good. But here's another problem, okay? So what happens when we get through the part and then we actually get through to where the hole is, right? We're going to be putting a considerable amount of pressure on this thing up until the point that we get through and we cut into the side wall of the hole, and then all of a sudden there's no material there, and so all of that force that we're putting on the part is going to just become a jerky movement that goes boom. And then what's likely to happen is that the bandsaw cuts the backside of the hole and mars it, which is not great considering all the time that we've already put into this thing. There's really no way to come back from that. It's just going to make your part look gross. So what we should do is set up some kind of like a hard stop in order to keep the bandsaw blade from marring the backside of the hole. So that's what we've got this parallel and the clamp there for. So all we're going to do is position the part in approximately, let's say, the center of the hole, just so we know that it's not touching the backside, but it's through the front side of the hole there. Bump this parallel up against the back of the part in that position. So something like that, and then clamp it down. And now the part will not physically be able to move past that point. So, I don't know, people always find interesting ways to mess things up, but, in theory, there's no way now to go too far. Okay, so that's a neat little trick. All right, let's go ahead and reposition this thing so that we're following that line. Yeah, just line the center of the bandsaw blade up with the center of that line right there. Okay. Again, adjust this up and down so that you get as close to the part as you can, while still having enough clearance. Okay. Go ahead and turn the bandsaw blade on. So we're going to lubricate the bandsaw blade with this kind of wax lubricant. Pretty gross looking. So you just go ahead and stick that into the blade, and you'll see that the wax will start to adhere to the bandsaw blade teeth, and it comes around again. You can see where it actually touched. That's all you got to do. Position the part, and instead of pushing directly with our hands, we're going to use these little blocks right here, just so that if we slip or anything like that, we're not going to run the risk of jamming our fleshy little fingers down into the bandsaw blade, which could hurt a lot. All right, here we go. Now, it does take a fair amount of effort to get this to go. So you're trying to so with my left hand, I'm keeping the part up against the guide rail, and with my right hand, I'm just giving it enough force to keep cutting. Almost there. Oh, there we go. Yeah, so you can see it really popped out there, and if we didn't have that stop set up, then I would have very easily just messed up the backside of the hole. All right, go ahead and pull this out. Whoop. Okay, let's see what that did. Brush this off. Now you can actually see on here that the line isn't very straight. And that could be because of a couple of different reasons. One is that I wasn't following the guide rail very well, or I wasn't pushing up against the guide rail. Or another possibility is that, well, another possibility is that this surface here is crooked, right? It's not perpendicular to the other surfaces. But what's more likely, I think, is that this bandsaw blade is a little bit dull, okay? When these start to dull, they start to wander around a little bit and start cutting curves or cutting at angles, all right? So that's just how, that's what happens when they start to wear, okay? This is still acceptable because we're still going to go in and remove all that material with the milling machine, right? But if this were, if I was trying to do any kind of more precise, finer work with this, this would be totally unacceptable. It's really not following that line very well at all. Okay, let's set up for the next cut. Make sure it's all nice and clean. Get all the chips off of there. So let's set up for the next one. That's going to be this cut right here. You can see how nasty that cut is. There's a nice big burr right there. Okay, so if I had done this side first, well, in order to do this side now, basically that burr right there would be up against the guardrail, and it would be difficult to get a really good location off of the guide rail. Okay. All right, so let me go ahead and position the parallel first. So that's about where I want it to stop, right there. Let's go ahead and lock the parallel down at that position, bumping up against the back of the part. Okay, now I can set the position of the guide rail. Just like that. Okay. A little bit of that lubricant. Set the part back up. Okay, here we go. Almost there. And boom. Okay. There we go. So all that material's gone. We didn't have to cut all this material in order to remove it, right? We only had to cut, that thin little kerf, right, just where the bandsaw blade was actually cutting. So we removed all this material without having to actually cut it. And so that's where the efficiency of the bandsaw really comes into play. Okay, so there we go. And you can see that, yeah, definitely that did not cut super straight. So that's something that, well, I think I'm just going to have to replace this bandsaw blade. But that's for another day. It goes without saying that you should clean everything off, both your part and the bandsaw, so that the next person has a nice clean machine to use, like so. So all this just goes off onto the floor. And then the floor gets swept at the end of the class period by whoever actually used the bandsaw that day. So what to do with the remnants here? We actually don't scrap these. We save them in this little bin right here. These actually get used for like sacrificial test pieces when we're doing heat treatment in the third semester, well, end of the second, beginning of the third semesters. So yeah, don't throw them away. Just go ahead and put them in the bin. And there we have it. It's starting to look more like the picture, huh? Inside of that reamed hole looks pretty good. Surface finish is nice. Now all we have to do is remove some material from these two bandsaw cut surfaces here to get it to blend tangent to the reamed hole. And then the inside surfaces will be done. Then we just have to finish the outside. So only really 2 steps left to go. So there's part 4 and part 5 of the demonstration video, and then we're done. So that's it for this video. Thanks.